Hi, my name's Elijah Higgins, and I did my presentation over communities and crime. Communities are places with groups of people who share common attitudes, goals, and interests, which creates a sense of fellowship, and yet communities are often plagued by those with bad intentions, leading to crimes and felonies. The data I got came from the UCI Machine Learning Repository, and it's the Communities and Crime dataset. It has 1,994 data points and 128 attributes selected for their potential connection to crime. And this is crime as defined by the US. It's violent crimes as defined by the US, which are murder, rape, robbery, and assault. This data was gathered from the 1990 US Census and the 1990 US Limis Survey and the 1995 FBI UCR Division. The dataset can be obtained by searching communities and crime in the UCI repository. My research question for this data is, do race, income, and police department demographics affect the number of violent crimes within a community? And you can see there my null hypothesis is that all of the betas are equal to 0, and the alternative is that not all of the betas are equal to 0. I chose to include the police department demographics given the current state of race and police in the US. My secondary hypothesis test is the belief that the number of people living under the poverty line will have a positive impact on the number of violent crimes. And there you can see the null hypothesis is that the beta is 0, and the alternative is that the beta is greater than 0. So dataset characteristics, all of the data I used is numeric data, which was originally normalized by the curator of the dataset into a decimal range of 0 to 1 using an unsupervised equal interval binning method. I used 319 of the original data point because not all of the police departments were part of the Limis survey, and so they did not have data for the percent of race percentages in police departments. And here we've got a table of all of the variables. We've got the response variable Y is the number of violent crimes per 100,000 people, and then we go into the independent variables. We've got population, breakdown of race, a breakdown of race in police departments, and a breakdown of race for per capita income, as well as the number of people living under the poverty line. So our preliminary analysis, it shows only 3 of the parameters that I chose had any significance, and the model only explains 55% of the data. This made me think that maybe I hadn't chosen enough of the 128 original parameters, but these were what would answer my research question, so that's what I chose to go with. This is from that first regression, and we can see the normal QQ plot shows a lot of abnormalities, a not very straight line, definitely some curves, and so I did a Shapiro test, and we get a very low p-value, which means that the data set is showing some normality issues. And we also have here some of the residual plots for each of the parameters, and we can definitely see some curves and some problems there. So we're going to have some non-constant variance problems later on. So now on to building a better model. I began by transforming the Y. I did a box-Cox transformation in an attempt to fix the normality problem. And the code tested a sequence of transformations on Y and found that the power of 0.45 produced the best model. As you can see on the right there, 0.5 was within the values that were good to use. So for simplicity, I decided to take the square root of Y as the transformation. And then so I rechecked the QQ plot, and it definitely looks a lot more linear, a lot straighter and along that line there. And I did the Shapiro test again, and the p-value increased greatly. So originally it was 2.4 times 10 to the negative 6, and after the box-Cox transformation it was 0.005, so a great deal more normal data. Next, I went on to choose which parameters would produce the best subset. So I performed both of the best subset and stepwise regression algorithms to choose those parameters. Both parameters ended up choosing the same 5 parameters, and as you can see on the top left, we've got the results from the best subset algorithm, and you can see it's The one highlighted with 5 parameters has the lowest CP, the lowest AIC, and the lowest PRESS-P, which is really good. And so the new model parameters are now % Hispanic, % African American, % Caucasian, number of impoverished people, and per capita income of African Americans. So after choosing those parameters, I reran the diagnostics, and the normal plot didn't change very much. The p-value increased a little bit, which was a good sign. But now we're looking at the residuals for the parameters that we've chosen, and we're definitely seeing some non-constant variance, especially in the % Black and in the number under the poverty line. So next I went ahead and decided to take out the outliers and influential points if there were any. The influential plot down there gave these 5 points on the top as potential influential points. And so to check for outliers with respect to x, I calculated the 2 times h bar to be 0.0313, and therefore the points 11, 19, 21, and 169 were outliers and could be tossed out. 0.105 passed the test for x outliers, y outliers, and Cook's distance, so I left that one in. And here we can see the 2 summaries of the models with and without outliers. The one without outliers has an increased R-squared. We go from a 0.578 to a 0.595, and we also see great changes in the parameter estimates, as well as the t-values and the probabilities, p-values there. So multicollinearity hasn't been an issue so far in this data set, and I think that's because of the way the original data set was normalized. However, I went ahead to check that with the variance inflation factor, and as we can see, none of the parameters have a VIF that exceeds 10, so we don't have an indication of any excessive multicollinearity. Now, in order to fix the non-constant variance problem, I went ahead and did a weighted least squares regression, and the top table shows the curvature test for residuals of the model before the weighted least squares, and the bottom shows the curvature test results after the weighted least squares. And so after, we can see a significant increase in all of the p-values for each parameter, showing that it helped to really fix the non-constant variance there. And so now we have our final model, which we can see there at the bottom, and we can see the summary of it on the right. There we ended up with R squared of 0.639, which is pretty good. We started off at 0.55, and in the middle we can see an analysis of variance table, and on the left we have the k-fold cross-validation, and from that we can see that the root mean square is 0.137, which is pretty good. So now to use that model to answer our research question, we call the research question there. To answer this, I went ahead and did a global F-test, and so we have our F-test statistic is the MSR over the MSE, which we calculated using the numbers from the analysis of variance table, and we got a value of 112.1, and then the critical F value is calculated there to be 2.24, and so we can see, since the F-test statistic is so much higher than the critical value, that we can reject the null hypothesis, and not all of the betas are equal to 0. And now for our second hypothesis test, call that there. To evaluate the effect of a single parameter, we know that the F-test statistic is equal to the t-test statistic squared, which we can get from the summary of the model there. And so we calculate that value to be 22.668. And then the critical value there is calculated to be 3.87. And so clearly the F-test statistic is a lot higher than the critical value, and so we can reject the null hypothesis, and we can say that the number of people living under the poverty line will have a positive impact on the number of violent crimes within a community. So our conclusions, the initial model showed signs of non-normal data distribution and non-constant errors. In an effort to fix the normality issues, we performed a box-Cox transformation on the dependent variable y, which greatly reduced the prominence of those errors. And then to fix the non-constant variance, we did a weighted least squares regression, which fixed most of those problems too. And while at the end the model wasn't completely normal and all of the variance constancy issues didn't go away, I think it fixed them enough that we could use them to answer the hypotheses that I had proposed earlier. So our initial model started out with 12 parameters, and our final model ended with 5. And from the model, we can see it doesn't paint a very pretty picture of how race and crime work in America. But one thing to keep in mind is that crime, especially violent crimes like rape, murder, assault, and robbery, are very complex issues, and they have a lot of different factors that go into them. So a model that just depends purely on race or any other socioeconomic factor isn't going to accurately capture the whole situation. But it is interesting to know how the per capita income has such a dramatic role in decreasing violent crimes, and also, on the other hand, how the number of impoverished people, people that live under the poverty line, has a positive impact on the number of violent crimes within a community. Thank you.